This next section we're mainly going to talk about the energy of a capacitor, but I wanted to show you this diagram of a capacitor charging first. So the capacitor's plates start out with a neutral charge, which we have here, the equal number of positive and negative charges. So the battery, we know now that the electrons are the mobile species in a conductor. So the battery forces electrons onto the plate, and the presence of the negative charge on this plate means that the electrons are driven away from the other plate because they're allowed to return to the battery. And so even though we don't have positive charges really moving, we're going to get to this in the next chapter, we depict them as a mobile species. We're going to get more into that later as well. So what is the energy stored in a capacitor? Because that's really the whole point of a capacitor, is to store energy. So from very basic principles, it's the amount of charge times the change in voltage between the two plates times 1/2. And as you can imagine, this is coming from integration. We're not going to derive this equation because it requires integration, so we're just going to take it for what it is. And if we use Q times delta, Q is equal to C delta V, we get two other forms of the equation, C 1/2 C delta V squared, or C squared over C. This one's often written as Q squared over 2C, but I wanted to keep the same form here as the 1/2s on each one of them. And where are capacitors used? You might want to say, okay, why do we care about capacitors? Well, capacitors are used in pretty much every electronic device. The main place that you might see them used in your life are camera flashes and defibrillators. When you turn your camera flash from off to on, often, especially with a just point and shoot camera, standalone camera, it takes some time before that flash can become active. Because what's going on is we're charging a capacitor, and we need to charge a capacitor because a capacitor can release energy much more quickly than a chemical battery can do so. So a capacitor is a form of energy storage in case we can charge it up, remove it, and then use it to power something, which I believe you should be doing in laboratory at some point. So other uses for capacitors are electric filters, timing circuits, and power conditioning, all of which are used in all of our electronic devices. Now we're not going to get into these more complicated circuits, but these are really useful devices. Alright, now we're going to look at some math associated with the energy in a capacitor. So here we have a parallel capacitor consisting of two square plates, 10 centimeters on a side, so that area is going to be 10 centimeters times 10 centimeters gives us 0.01 meters squared, an air gap of 0.75 millimeters, so that's going to be 0.75 times 10 to the negative 3 meters. And we want to figure out the charge on the capacitor when the potential difference is 150 volts. So all this information looks very much like we're going to find the base capacitance. It doesn't say anything about any special material in there, so we're going to use our base capacitance. So C0 is equal to our permittivity of free space times area over D. So that's going to be the 8.85 times 10 to the negative 12th coulomb squared over Newton meter squared times our area of 0.01 meters squared divided by the distance between the plates times 10 to the negative 3 meters. And that gives us a value of 118 times 10 to the negative 12th coulombs. Negative 12th is pico. And then we want to find what's the charge on the capacitor when the potential difference is 150 volts. So we're going to use our capacitor equation to find that. Q is equal to C delta V. So 118 times 10 to the negative 12th coulombs times our 150 volts gives us 1.77 times 10 to the negative 8th coulombs, or 17.7 times 10 to the negative 9th coulombs. So that means it's 17.7 nanocoulombs. And then what is the energy stored in a capacitor? Well, now we can use the energy equation, and we have our choices. We're given delta V in the problem, so we're going to choose one of these two with delta V in it. And then we also know the Q. So we just figured that out. There's my Q, so I'm going to use the one with Q in it. We could use the one with C in it, but it doesn't matter. We should get the same answer either way. I'm going to use the one with Q in it. Q delta V is equal to 1/2 times that 1.77 times 10 to the -8th coulombs times the 150 volts gives me 1.33 times 10 to the -6 joules, or 1.33 microjoules. Here's all those values a little nicer written out. And then here is a problem for you to go ahead and give it a try. So this is one of the applications. This is a defibrillator, and defibrillators need to charge up before they're ready to use because they're basically charging a capacitor so that it can deliver the right amount of energy, the right amount of voltage very quickly to the patient. So here we know the heart defibrillator delivers 400 joules of energy to the electrodes by discharging a capacitor initially at 10,000 volts. So we're given the amount of energy. So this is my delta U and the voltage. Now you go ahead and see which equation you want to use and be able to figure out what the capacitance is. Okay, so hopefully you paused the video while you did that. So we know delta U, so that's a good equation to use. We know delta V, so we have these and this one, and we want to find C. So this is the thing we want to find. So we're going to use that version of the equation. So U is equal to 1/2 C delta V squared. And so that means C is equal to 2U over delta V squared. And 2 times 400 joules over 10,000 volts gives us 8 times 10 to the -6 farads, or 8 microfarads. So that's a fairly common capacitor. It's not big, not small, kind of an average capacitor value, so not too big.